At this point in section 2.1, we've learned that a set is a collection of elements with a common characteristic. We've also learned that we can express sets in roster notation or set builder notation. And we've learned about a couple of special sets, such as the empty set or the set of natural numbers. In section 2.1.3, we will learn how to express set membership with a special symbol which looks like an E. This symbol represents set membership and can be read is an element of. So when I see that symbol, I'm going to translate it into this English phrase, is an element of. Now, if that symbol represents the phrase is an element of, what do you suppose that symbol with the slash through it represents? It's simply the negation. We would read this is not an element of. In the same way that you can negate an equal sign by slashing it through, making it not equals, anytime you see a slash through a particular mathematical symbol, it simply negates that symbol. So we have the symbol for is an element of and the symbol for is not an element of. Let's practice using this new symbol. Example 7. Determine if the following statements are true or false. Example A. R is an element of the set containing A, B, C, D, ... Z. Notice this is a finite set. That means it has a beginning and it has an end. This ellipsis simply means that the pattern established by the first few elements in the set continues. So we can interpret that to mean all of the letters between D and Z. So we're trying to determine if R is an element of this set. Well, R is a letter between A and Z, and it would fall somewhere in this ... So this one is a true statement. R is an element of the set, which is the alphabet in roster notation. Let's look at the next example. 10 is not an element of the set containing elements 1, 2, 3, 4, 5. Notice that is a finite set given in roster notation. There's only 5 elements, and 10 is not one of them. So this is a true statement. Example C. 2 is an element of the set of all x such that x is an element of the natural numbers and x is odd. Notice we are dealing with a couple of new symbols here. We have our element or our set membership symbol. We have the symbol for the natural numbers, and we are dealing with set builder notation. Let's try and read that start to finish again. 2 is an element of the set of all x such that x is an element of the natural numbers and x is odd. So this part simply tells me that I'm dealing with a counting number. That means I can rule out fractions, I can rule out negative numbers. And x is odd. Well, let's rewrite this set in roster notation so we have a better idea of the elements of that set. The natural numbers that are odd include 1, 3, 5, 7, 9. Looks like we're dealing with an infinite set, so we will express that as ... and close our curly braces. Is 2 an element of that set? No, 2 does not belong to that set, which makes this statement false. Moving on to example D. We read, 5 is not an element of the set of all x such that x plus 3 equals 9. Now I'm going to throw a little bit of algebra at you here. Don't worry, we're not going to do much algebra in this class, but I think you can handle this one. If I look at the equation x plus 3 equals 9, I can solve that equation by subtracting 3 from both sides, and I end up with the solution x equals 6. If I take 6 and I plug it back in for x, 6 plus 3 on this side is equal to 9. So we have a balanced equation. So another way of writing this set is simply the set containing the single element 6. That's what we call a solution set, the set of solutions to that equation. The statement here says 5 is not an element of the set containing 6. Well, that is a true statement. The last example deals with the empty set. Example E says 0 is an element of the empty set. Now, because we associate the empty set with 0 because it has 0 elements, you might want to jump to a conclusion and say that this is true. But notice this is implying that the empty set has an element, and we know the empty set has no elements. So this is a false statement. So that's a very good exercise on a lot of the notation that we've learned up to this point. Let's try example 8. Express the set of all x, such that x is an element of the natural numbers and x is less than 200 in roster notation. Now remember, in roster notation, we begin with a set of curly braces, and then we just give the roster or the list of elements that belong to that set. So we are dealing with natural numbers or counting numbers, and the first counting number that is less than 200, of course, would be 1. And we're going to count our way up to 200, right? Or at least less than 200. That's going to be a very long roster. So I'm going to save some time and show this pattern of counting continues with the ellipsis, ... until we get to the very last element in the set. Now, is 200 the last element in this set? Nope. This says x, This says x must be strictly less than 200. So the last element in this set is 199. So we have listed a very long set in roster notation, but we took a shortcut with the ellipsis or the ... Example 9. Express the following sets in set builder notation. The first set we have is the set containing elements 1, 2, 3, and 4. Now remember, in set builder notation, we start with the curly brace. We have a representative of the elements in the set. We can just use x in this case, and the vertical bar, which reads such that. Notice we are dealing with natural numbers. I want to be very specific that we are dealing with natural numbers. That's going to rule out fractions. That's going to rule out negative numbers. That's going to rule out irrational numbers. So we are only dealing with counting numbers. And these values are between 1 and 4. So we could say x is greater than or equal to 1 and x is less than or equal to 4. Another way to write that, maybe a little more efficiently, the set of all x such that x is an element of the natural numbers and 1 is less than or equal to x, less than or equal to 4. So here I see the number x between and including 1 and 4. Example B, the set containing 18, 19, 20, and 21. In set builder notation, we could say this is the set of all x such that, notice we are still dealing with counting numbers, so we need to write x as an element of the natural numbers, and we can trap those values between and including 18 and 21. Just to show you that there's not one right answer, there's not one right way to do this, there's other options. You could also say the set of all x such that x is an element of the natural numbers, x is greater than 17, and x is less than 22. Notice I'm going from an inclusive inequality or an inequality containing an equals in this example to an strict inequality, or one that says the number has to strictly be less than 22 but not including it. So there's some variation. You do have some options on those examples. The last one, the set of values containing 1, 3, 5, 7, 9. Notice we are not dealing with negative numbers or fractions, so we're going to specify we are dealing with natural numbers. The set of all x, such that x is an element of the natural numbers. And what common property do you notice about those numbers? Clearly, they are odd, and x is odd. That happens to be an infinite set, but we have expressed it concisely in roster notation with the ... and using this description in set builder notation.